Welcome to the electrostatics lesson on capacitors and circuit basics. We start with a discussion on capacitor. What is a capacitor? A capacitor is an electrical device used to store energy electrostatically in an electric field. We'll talk more about this as we go, but these are devices used in a wide variety of circuits. But their function is to store energy electrostatically in an electric field. A capacitor's ability to store charge is called capacitance, and that capacitance is dependent on a number of variables. In this first equation that we see here, capacitance, capital C, equals epsilon 0, which is a constant you'll find on your reference table, times the area, and the area referred to here is the surface area. And you'll recall that in electrostatics, surface area is directly proportional to an object's ability to store charge. The larger the surface area, the more charge that can be stored on that object. So epsilon 0 times area, A, divided by D. And in this equation, D is the plate separation. A capacitor typically is a pair of thin metal plates separated by some distance D, and those plates would have some surface area. They can also be discs that are parallel to each other, much like what we talked about with the Millikan oil drop apparatus. So a capacitor's ability to store charge, capacitance, equals epsilon 0A divided by D. It is also equal to the ratio of the charge on each conductor, on each plate that is, divided by the potential difference V between the plates. So you can set up a nice ratio of all these variables, and if they asked you for the impact of changing one of these variables on capacitance or any of the other variables themselves, you would be able to figure out those relationships. Be careful with A. If A are disks and they make a change to the radius, you know, of course, that the area would be pi r squared. Otherwise, if they're rectangular and they change the length of the width, you would take that into account as well. The unit of capacitance is the farad, abbreviated capital F. And typically you would see capacitors between picofarad, which is 10 to the negative 12, and millifarad, which would be 10 to the negative 3. Most typically we see them as microfarads or nanofarads. Moving on, we want to talk about the equation to calculate how much energy is stored in a capacitor. And since stored energy is potential energy, it makes sense to us that the symbol for the energy stored in a capacitor would be capital U. We give it a subscript C to remind us that that potential energy is stored in a capacitor. The equation for that is 1/2 Q times V. If we use the equation C equals Q over V and we solve it for Q, Q would be C times V, and we substitute that into the first equation, we get another derivation for the energy stored in a capacitor, which would be 1/2 CV squared. Being energy, of course, both these calculations would result in units that are in joules, which is capital J. Okay, now the next discussion is a segue between an electrostatics discussion and a current electricity discussion. So this topic, capacitors, really bridges the electrostatics unit to our current direct current electricity unit, which will be next in our series of study. So what you're going to learn here in the next part of this video is the difference between a series circuit and a parallel circuit, key points to keep in mind, and how they impact a capacitor's ability to store charge in a circuit. First, most important thing for you to know is what is a series circuit. And a series circuit is one in which there is only one path for the current to flow. Series circuit, only one path for the current to flow. What I would like you to do is to start off here by just drawing this circuit shown on the left here. Let me explain each of the components here. This circuit has a potential difference created by a battery. This is a symbol for a battery. Long line, short line, long line, short line. And in the battery symbol, the long line represents the positive terminal of the battery, and the short line represents the negative terminal of the battery. In this particular circuit, we have three capacitors connected in series. We have capacitor C1, and the symbol for capacitor is a set of parallel lines representing parallel plates. We have capacitor C2, and we have capacitor C3. It's not said to us whether or not these capacitors all have the same capacitance. It doesn't matter, it's just to create an understanding of what a series circuit is. But you can see, if you followed from the negative terminal, the flow of current has only one path for the current to get back to the positive terminal of the battery. Understanding that current would be the flow of negative charges. It would be repelled from the negative towards the positive. So there's only one path in this circuit for the current to get from the negative terminal back to the positive terminal. What happens, of course, is then the battery has chemicals in it or some other method by which to do work to put electrons back on the negative terminal and to keep the current flowing at a constant rate. The one huge advantage of a series circuit is the fact that the current remains constant wherever you are in that circuit. So the total current leaving the battery, IT, is equal to the current passing through capacitor 1 is equal to the current passing through capacitor 2 is equal to the current passing through capacitor 3. The current remains constant in a series circuit. It is the advantage, quite frankly, the only advantage of a series circuit. Current is the rate of charge flow. Well, as soon as we heard the word rate, we knew that time was in the denominator, and charge, we assign a capital Q value, so I equals Q divided by T. Current is the, if you want to think of it this way, the number of electrons that pass a point per unit time or per second. Okay, so it's coulombs per second. Well, if we take into consideration that capacitance is charge divided by potential difference between the plates, if the current remains constant, then that means the rate of charge flow remains constant. That means for capacitors in series that the charge on each plate in a series circuit is also constant, no matter the size of the capacitor in that circuit. It's really important. Since all three have the same current passing through them, all three have the same rate of charge flow, and since the identifying factor of a series circuit, besides the fact that there's only one path for the current to take, is that the current remains constant, that lends to the charge remaining constant in each capacitor, despite how much ability to store charge there is for that capacitor. Okay, really key point here. Lastly, for a series circuit, if we wanted to know what was the equivalent capacitance of the entire circuit, another way to say that is what is the total capacitance for the entire circuit. We take the reciprocal of the total is equal to the sum of the reciprocals of the individual capacitors in that circuit. So on your reference table, you'll see 1 over CS, which is the 1 over total capacitance in series, equals 1 over C1 plus 1 over C2 plus 1 over C3, and the dot 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 just simply is there in case there are more capacitors than that. Now, a nice little trick to remember is that because of this reciprocal relationship, that the total capacitance in series will never be greater. In fact, it will always be smaller than the smallest capacitor in your circuit. So if C1 were 2, C2 were 4, C3 were 6, before you even start calculating, you already know that your total capacitance will be less than 2 because 2 is the smallest capacitor in the circuit. Nice rule of thumb to remember. All right, let's move on to discussing parallel circuits. It should make sense to us that a parallel circuit is one in which there is more than one path for current to flow. Let's start by drawing the circuit itself. Again, we see in this circuit a potential difference supplied by a battery, potential difference V. And this time, as the current leaves the negative terminal of the battery, it gets to this spot right here, which is called a junction, and the current splits. Some of the current goes up through this branch through capacitor C1. The rest of the current continues to travel, gets to this junction, splits, some of it traveling through capacitor C2. The rest of it comes up through capacitor C3, then joins back up with the current that passed through capacitor C2. That total for C2 and C3 joins back up with the current that passed through capacitor C1, and then the total amount travels back to the positive terminal of the battery. The battery does work to put electrons back on the negative terminal, and the current continues to flow through the three branches. The amount of current that flows through each branch is going to depend individually on the capacitance C1, C2, and C3. If they're identical, they would take the total current and split it equally. But if they're not identical, then they will split that current proportionally. The key factor for a parallel circuit is the fact that the total voltage supplied by the battery, which we would call VT, remains constant. So each capacitor in the circuit, in fact, any electrical device in the circuit, whether or not it's a capacitor or not, all get the same voltage. So C1 gets the total voltage, C2 gets the total voltage, and C3 gets the total voltage. By inspection of C equals Q over V, what you then note is that the capacitance, the ability of the capacitor to store charge, and the amount of charge stored on it are directly proportional to each other. So the larger the capacitor, the more charge it will store on its plates. To figure out the total capacitance of capacitors in parallel, you simply add, this is incorrect, CP equals C1 plus C2 plus C3 ... So make that adjustment. I'll have to make that change here when done recording. CP equals C1 plus C2 plus C3. So the total capacitance in parallel is equal to the sum of the individual capacitors in that circuit. If you have any questions, make sure you write them down and ask when we discuss this topic in more detail in class tomorrow.